Hi guys, welcome. Today we'll be talking about scientific notation. And scientific notation is just basically coming from the idea of how do we take really big numbers or really small, infinitesimally small numbers and rearrange them so they're in a certain type of form. That can be easily read across all languages, all countries, and all methodologies of basically anything to do with science or mathematics. Okay, so scientific notation is a number written in the form of a times 10 to the n, where n is an integer and a is between 1 and 10. Now, if you notice the notation on a, okay, a can be equal to 1, according to our information from last semester, but a cannot be equal to 10. Okay, so you have to understand, so our upper boundward limit would be like 9.99999 something something something. Okay, now there is a proof out there that says that 9.99999 can be rounded up to 10, but we're just going to assume it's going to be like this for right now. Okay, so please understand that when you are working on this stuff, that it's going to be pretty simple to work with. I don't know where that 9.99 repeated went. Okay. Alright, so taking a look at this right here. Okay, we have everything all set up like we wanted. Okay, here's some examples of how this works. Okay, example, 35 million becomes 3.5 times 10 to the 7th. 1,200 becomes, or 1,200, that's most commonly known here in America, becomes 1.2 times 10 to the 3rd. 4 can actually become 4 times 10 to the 0, and you'll understand where these numbers are coming from, these exponents. 19 becomes 1.9 times 10 to the 1st, although technically smaller numbers such as these ones right here, 4 and 19, we won't mess with too much, but if you had to get really strict, you could write it like this. Okay, 0.000123 becomes 1.23 times 10 to the negative 4th, and 0.00007008 becomes 7.008 times 10 to the negative 6. Okay, now you're probably wondering, how did they get all these weird places for all these numbers and stuff? Okay, so when you move the decimal n places left, okay, you make the exponent on the 10 a positive n. So you make it a positive number. So we move the decimal 1, 2, 3, 4, 5, 6, 7. 7 places to the left, so that's where we get the positive 7. On here, we move the decimal 1, 2, 3 times for a positive 3. Okay, we didn't move the decimal at all because it's already in its form. So that's where we get the 0 from. And right here, we move the decimal once to be behind the first number that's not 0, and that's where we got the 1 spot. Okay? All right, now, when you move the decimal to the right, a certain amount of n places, you make the exponent on the 10 a negative n. Okay? So in other words, we're going to be moving this to the right 1, 2, 3, 4, and we stop behind the first number. We don't go any further. We stop behind the first non-zero number. Okay? And so that's where we get the negative 4 from, and on this one we go 1, 2, 3, 4, 5, 6 spots, and that's where we get the negative 6 from. Okay? Now, when you are working with numbers that are all kinds of out of whack, like let's say you had 237 times 10 to the 5th. Oh, let's get that time sign in there. That might be important. 10 to the 5th and 34.2 times 10 to the 2nd. No, let's make that bigger. Let's make that to the 7th. Okay? All right, and then we have, let's go 456,000 times 10 to the 3rd. Okay, if you were trying to order this from least to greatest. Okay, when you're working with it, to put it in scientific notation will actually make your job a whole lot easier. Now if you notice, I already have exponents here, and it already kind of looks like it's in scientific form. But if you notice, these numbers are not between 1 and 10. So what I'm going to do is I'm going to move the decimal and add to these. So now when you're moving the decimal left n places, make the exponent. So we already have an exponent here, so we're going to be adding to it. Okay, so we'll be adding to it in this one. Now if we were going the other way, you would be exactly correct in saying we would be subtracting. So if you move right, you subtract. If you move left, you add. Okay, so on this one we move it twice to the left. Okay, so we add 2 with this, and so this number becomes, now I can look at it a little bit more objectively, 2.37 times 10 to the 7th is that number. Okay, now on this one, I'd be moving the decimal 1 place to the left, so I'd only be adding 1 here. Okay, so that would become 3.42 times 10 to the 8th. Okay, and this one, even though it looks like it's the biggest number to begin with, 1, 2, 3 spots. So I add 3 to the 3, and so this becomes 4.56. And you can leave off the 0 if you want. I mean, it's just seriously significant figures. Okay, all right. And what you can do is notice, oh, hey, only one of these is actually the smallest, and it's going to be the one with the smallest 10 power. So first off, it's going to be this one, then next it's going to be this one, and then next you can rearrange it to be this one. So from least to greatest, it goes in this order. Okay, all right, and because you have it in scientific form, you can correctly judge the numbers as to which ones has the greater significant value, or the greatest value out of a whole bunch of numbers that are big and small. Okay, all right, that's it for scientific notation. Oh, and another side note, when you're doing calculations in science and you're using scientific notation, we're going to learn tricks later with the rules of exponents that's going to make our job a lot easier than just doing some multiplying and dividing with really large numbers. That actually helps us to get some really cool numbers, so we can actually work with this stuff pretty easily. Okay, you guys have a wonderful day, and I will talk to you later.